basically getting.
Good morning, Bears. We are day 2 of thermal energy. Remember, we got a problem to solve. We need a heating system. Those kids look a little cold to me in that school, and we need to warm them up. We could use solar power. That's an idea. A lot of people do that. Solar energy comes down. I have solar panels right here on my house. Let's see if we can see them. Those are solar. Ooh, they're dirty. Oh boy, I gotta clean those off. That's a whole nother science experiment. When there's dirt, and then can the sun go through it? Believe it or not, the sun goes through it pretty good, but I need to get up there and do a major cleaning to get some more energy. So, looks like the school we're helping out is not using solar power that I've seen yet. And today, before we can help them, we need to know more about temperature, more about heat, more about thermal energy, more about molecules. Let's take a look at Ethan's slideshow. Did a great job. Look at this. Ethan has a molecule slide up top. That was Monday's homework. We can see that there's atoms. We have learned about atoms. I don't know if we think back to our health lessons, we were talking about atoms because remember H2O, water goes into cells. We can get starches into cells. We have amino acids. And so atoms connect together to make molecules. Molecules, an electrically neutral group of two or more atoms held together by chemical bonds. Molecules are distinguished from ions by their lack of electrical charge. Interesting. Know that. Then he has his other molecule that he moved to the top, and he even has a bonus heat slide. You can always do bonus slides. That's a great thing. And so he has all we needed to do yesterday. Now today, let's dive in to the sim. So scroll down at about 30, I believe. Around 34, depending on if you've added slides. There's a water molecule slide. In this unit, we will describe the smaller pieces that make up stuff by using the word molecule. In the sim, each circle represents one molecule. The sim portrays molecules on a much larger scale than their size in real life. Molecules are so small that scientists can only see them using powerful microscopes. Molecules are made up of even smaller pieces called atoms, but we are only focusing on molecules in this unit. Sometimes you will hear the word molecular used in this unit. That's just a way to describe anything related to molecules. Can you say molecular? Say it. Molecular. Molecular. Molecules. Molecules. Good job. The sim shows a small number of molecules so we can easily observe what is happening to them. The things around us, even very small things, are made up of billions of molecules. So remember, this is just a model. The molecules are tiny, and there's billions, and they're in everything, even things that aren't moving. It's an amazing world. And then there's something called a subatomic world. Check out Ant-Man, the movie. Craziness happens there. So things are made of molecules or other types of atom groups. Even things that might not seem to be made of anything like air are also made of atoms and molecules. So yes, molecules floating around in the air. Amazing. You observed that food coloring spreads out faster in warmer water than in colder water. Water is made of molecules. How do you think the molecules of the hot water might be different from the molecules of the cold water? Do they get bigger? Do they spread out? Do they move faster? Do they move slower? These are the questions we will ask. The sim allows us to visualize what is happening to the molecules of a thing. Now you'll use the sim to model the cups of water from the food coloring investigation. You will gather evidence to explain why the food coloring spread out differently in the two water samples. Now, here's where we're going to go to the sim. Now, these questions I've put into groups, basically a little bit different. So don't worry about that sheet if you can't read it. Just look at groups, and we have our basics here. Thermal energy, week 1, day 1, play with the sim. We're going to do that now. If the sim doesn't work, you can watch my video and get the same results, but it's much better if you play with it during this time period. And then we're going to read an article like we always do, doing some annotating. Remember those articles you have access to. You can highlight them, you can work on them, you can read them, you can turn them in. But for simplicity for both of us, in case they don't work, we basically cut and paste notes or use the article to answer these questions. What happens to molecules when they warm up? In absolute zero, would molecules move at all or just move very slowly? Then we're going to create a top slide temperature slide with definition and images. Pretty basic. Now there's our article, but first, back to the sim. Let's see if it works. On the sim, so come down to slide. It's approximately 41. It's right below the cups. Remember, if you add slides, it's going to look different. Find this slide says sim. Oh, I also put a sim link in groups. Not sure it'll work or not, but that way you can just check groups if you'd like. And let's see here. Add sample. It says run. Let's see what we do. Oh, add a sample. Please select the size for the sample. I like large. Confirm. Ooh, fantastic. So we have thermal energy and we have temperature. Now, 25 degrees Celsius, we might have to watch a little video on Celsius. The reason they came up with Celsius, or maybe they had it first, is 0 is when things freeze, 100 is when water, I should say water. 0 is when water freezes, like an ice cube. 100 is when water boils. So they thought that's a pretty easy scale. Now, Fahrenheit, what we usually deal with, water freezes around 32, 33 degrees, depending on the wind chill, and it boils, I don't even remember, we'd have to look it up, but it's a higher temp. And so they do Celsius. We'll have to do a little video on it to study. Now let's look up here. View kinetic energy. High. Those things are moving. View energy transfer. So here, remember, we can add another sample. Let's go large again. Confirm. And they're not touching, and I'm pretty sure we can, move them together to see things. Now we're going to get into this. We're just playing with the sim right now. I want you to go play with it right now. Now watch this. What happens when we do this? We increased the heat, cooled off the heat. So temperature 20 is colder, 25 is higher, thermal energy goes up. We can see all the different energy happening, and then we're going to play with transfer in a minute. But right now, you really didn't need to add this other sample, but you can if you want. You can just play with it, see what happens. So play with the sim right now, crank it up, make some observations. It should only take about 3 minutes, and then I'll come back and play with it so you can watch. Welcome back. So remember, we're not dealing with transfer right now, so this one I'm not even going to deal with. We'll talk about that in another lesson. Right now we're just talking about what happens when you crank the heat. I'm going to go to boiling. 100 is boiling. 100 degrees Celsius is boiling. Boiling, that's boiling water. Quite a bit of energy. 337 thermal energy. Wow, that's a lot. Hot, as my grandson says. Then I come down here, go all the way down to, let's go to 0. Let's go to frozen. Maybe they're calling that absolute 0. I'm not sure if they are, or if that's frozen. We're gonna do a little research on absolute 0. Are they still moving? Yes, but that's not absolute 0. That's 0. Let's find out about absolute 0 now. All right, so there's some questions we can ask. We're not going to do that activity because we don't have that much time. But in general, let's share out. I'm going to ask a couple questions in the chat, and let's just do a little release the Kraken. All right, get in your chat room. And the first question is, what happens when the temperature cools down? Do the molecules move faster or slower? Temperature goes cold. Cold equals faster or slower. Put it into the chat. Release the Kraken. Yes. When you drop the temp, molecules slow down. So opposite of that, when you increase the temp, molecules speed up. And then we can do this analyze later. It shows charts of what I've done, and that's going to come more into play when we do our sample B and we combine them together. Notice sample B didn't do anything. Straight line, purple, that's good practice for reading charts. Purple did the same thing. We have temperature, we have thermal energy. Notice the temperature and thermal energy track exactly the same. Green didn't do anything because I didn't have it. These charts will come into play later. I'm excited about it. Looks pretty good. All right, let's dive into, make sure we're recording still. I think we are. Dive back into Ethan's slide. So good job, Ethan. Thanks for letting me use your slide today. Remember, don't worry about that. Just do the directions in groups. Use the evidence from the sim to try to answer the question, how is something different when it's warmer and cooler? You can answer that if you want at the top, or just do the questions. After the sim, why do you think food coloring spread faster in hot water? Why do you guys think it spread? Because when things get hotter, its molecules are moving faster, things will spread faster. When things get colder, its molecules are moving slower. We get it. Now, let's go read this article about absolute 0. The article, let's see this, the article you will read will annotate is called Absolute Zero. You will read it to learn more about temperature and molecular speed. I'm interested. Then you'll answer some questions about it. Read and annotate the article Absolute Zero. Once again, you can just follow along in this video or go to groups if you'd like to do your own highlighting. You can open it and read along with us. Up to you. I recommend just reading along here. Remember, there is a hand in button here because when you guys actually log in, this is an active document that you guys can use. You can hand in, you can highlight, you can research. But for simplicity, we just do this in slides, and we will probably refer back to this as a close read tomorrow. So kind of pay attention now. We're just answering questions. Here we go.
Absolute zero. You've probably felt cold temperatures at some time in your life. Maybe you live somewhere with cold, snowy winters, or maybe you've just opened the freezer to grab a popsicle on a warm day. The temperature inside a normal kitchen freezer is around negative 18 degrees Celsius, 0 degrees Fahrenheit.
Okay, let's take a look here. The temperature inside a normal kitchen, by the way, always follow along when you have an audio. It's going to help you to become a better reader. Remember, you make the choice to get smarter every single day. You follow along, you read, you think, you get smarter. You daydream, you don't pay attention, you don't get smarter. The temperature inside a normal kitchen freezer is around negative 18 degrees Celsius, which is 0 Fahrenheit. That's interesting. I didn't know 18 was 0. But there are temperatures that get much colder than that. The coldest outdoor temperature ever recorded on Earth is 19. Okay, let's keep reading.
But there are temperatures that get much colder than that. The coldest outdoor temperature ever recorded on Earth is negative 94.7 degrees Celsius, negative 135.8 degrees Fahrenheit. In space, things get even colder. Scientists have measured temperatures as low as negative 270 degrees Celsius, negative 454 degrees Fahrenheit there. We know that the temperature outside can feel warm or cold to us. But what is temperature actually telling us? Temperature is related to the average speed of the molecules of an object or material. Molecules are constantly moving around. When an object's molecules move at faster speeds, the object has a higher temperature. When an object's molecules move at slower speeds, the object has a lower temperature. Is there a limit to how cold things can get? Yes. This is because temperature is determined by average molecular movement.
I don't like it that they skip over I love looking at pictures and reading the captions because that's how you learn a lot. Now notice they're showing here cold water. I don't see the difference between this picture and that picture, but I guess longer tails. So these longer tails are like, oh, they're bouncing around faster, bouncing around slower. The temperature of something is determined by how fast its molecules are moving. The molecules in the cold water on the left are moving slowly, as indicated by the short motion tails of the molecules. The molecules in the hot water on the right are moving more quickly, indicated by the long motion tails on the molecules. Notice we figured that out without even reading that. Oh, short means slow, long means long.
And there is a limit to how slowly something can move. After all, if something slows down completely, it just stops moving. What would happen if the molecules in a sample stopped moving entirely? If none of the molecules were moving, then the average speed of the molecules would be 0. This means that the sample would be at absolute zero, a temperature of negative 773.15 degrees Celsius, negative 459.67 degrees Fahrenheit. Absolute zero is the coldest possible temperature, the temperature at which there is absolutely zero molecular movement. Scientists realized over 350 years ago that absolute zero could exist, but nobody has succeeded in demonstrating it. It may not be possible to reach absolute zero, but that hasn't stopped scientists from trying.
Wow. So check it out. If you're in your own doc, you can actually answer these questions. Which of the following would be true if something was at absolute zero? The molecules that make up a sample wouldn't be moving? The molecules that make up a sample would be moving very slowly? Or the molecules that make up the sample would be moving very fast? Which one do you think it is? 1, 2, or 3? Not moving at all, slow, or fast? Think about it. Put it in the chat if you want. Wouldn't be moving at all. And I didn't know that. I thought they always moved at some point. So absolute zero means absolute zero movement. And that makes sense, right? Now that we know temperature is measured by movement, absolute zero temperature, absolute zero movement. If the molecules of the sample speed up, what else happens? The temperature of the sample decreases, the temperature sample increases, the temperature sample stays the same. I think we know when things start to move up and move faster, the temperature increases. All right, fantastic. So now we can get to our basics for the day. Let's go to groups. What happens to molecules when they warm up? Describe that in a top slide. In absolute zero, would molecules move at all or just move very slowly? Describe your answer based on the article. And then create a top slide, temperature slide, definition, images. And you know what? For that one, let's go ahead and why don't you research a little bit the difference between Celsius and Fahrenheit. When does water freeze and when does water boil? I'm going to add that in. When does water freeze? When does water boil? Research it and do the difference between Celsius versus Fahrenheit. I don't know if I can spell that. So that gives us a nice little slideshow to learn some things. All right, let's do this. We're in Zoom. If you need help, let's get some of this work done. Best time to get your work done is in class when I give you this little bit of time. I think we'll have a little bit of time left. We shall see. All right, have a great day, Bears. Let's do this.